so today we're going to look at, up to now, I've told you that there are two types of force situations. One where the force is applied horizontally. You know, I think I have a Kleenex box up here, and we were pushing sideways on it, right? So you remember that I said you're looking at it sort of like sideways, horizontally. Ready to go, Colby?
Yeah.
And the other way would be to like looking top down, right? You're sort of like a bird's eye view kind of. Well, there's another similar situation, and that is the horizontal component of force. Okay? So what happens is the applied force is at, and rather than being straight sideways, the applied force is at some angle. Okay? So does all of that, let's just say that this applied force is, we'll say, I don't know, 100 newtons. Does all of the 100 newtons go into moving it sideways? No? How come? Because it's at an angle. Okay? Now that diagram is going to appear a little bit later. I should point out, in the solutions in my youth, I used to call it FH, where H stood for horizontal force. And then I realized a few years back that students were confusing it. They didn't realize, they thought it was a different force. And I had kids using FA and FH in the same one. So I've gone now to, so in the solutions it says FH, but now I'm using this terminology, FAX. Okay, so it's the X component of the FA. The X component of the FA. Do you want to just turn the light on over there? Thanks. Perfect. So the idea of components is an important thing that's going to come up in grade 12 as well. So this is sort of your first introduction to that. Okay, so as we were saying, in a situation like this, not all of the applied force goes into accelerating the object horizontally because of that angle. And please don't draw the diagram again, you guys, just because it's on another slide. Okay? Not all of the applied force goes into accelerating the object horizontally. And in fact, do you even need to write any of that down? All you got to do is know it. Only the horizontal component acts horizontally and contributes to the acceleration. Okay? So I'm really only concerned with what percent or what value, how much is this FAX. And again, the FAX stands for X component of the applied force. How much of that applied force is actually sideways? The value of FH or FAX is dependent upon the applied force and the angle. And obviously, if the angle was right down to 0, well then the FA would equal the FAX, right? And if the FA is straight up, how much FAX is there? None. Right? The angle's 9. If the FA is straight up, well then there's no sideways at all, right? So it does depend upon this angle in here, which we of course call theta. Okay, I'll pause there for a second. Probably not a whole lot of that is necessary to write down. How am I going to find, if I give you the angle, are you going to be able to find FAX? If I give you the FA and the angle, can you do that? Probably. What kind of triangle is that, Jason? Right triangle, which means you're going to be able to use good old trigonometry, sine, cos, and tan. Remember how much fun those were in grade 9? Grade 9 or grade 10? You didn't enjoy it? Maybe you didn't have the right frame of mind now. Couldn't remember which one was which. Oh, the sine and the cos, couldn't remember which one? Did they teach the old SOHCAHTOA thing? How can you forget SOHCAHTOA? I'll help you. Okay, so again, same diagram, please don't redraw. Suppose the FA is 100 newtons and the angle is 30 degrees above horizontal. So we've got 100 here and we got 30 degrees. That's all you probably need to draw, right? As Jason pointed out, this is a right triangle. The 100, the FA, is it the opposite, adjacent, or the hypotenuse? Hypotenuse. How do you know which one's the hypotenuse? What's the rule? And it is opposite the 90, that's true. And it is also the longest side, I heard someone say. Right? It's the hypotenuse, yeah. It's the one that's at an angle. Okay, so that's our hypotenuse. This is our angle. Which one is this one? We'll see if Anna can do it. Is it the adjacent or is it the opposite? Is it adjacent? Because it's touching. And you know what? Anna, you're not the only one. It's a big boat that you're in. A lot of kids have struggled with that. Okay, this is adjacent. The adjacent side is one of the sides that makes the angle. Right? Like, you notice how I didn't complete the triangle here? The adjacent is one of the ones that makes the angle. And the opposite is the one that solves it, or is opposite, right? It's like on the other side. It is not part of the angle. And adjacent is cosine or sine. SOHCAHTOA. Megan, what does the SOHCAHTOA stand for? What does the SOH stand for? You know? Never learned that, Jason? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. You learned that? Oh.
Like, two cats sat on an orange and
Two cats.
sat on an orange and held hands.
And how does that help?
Each letter, it just goes up.
Oh, it goes this way. Two cats sat on an orange and held hands. Okay. And then you...
Stupid if you remember it.
It is stupid. The stupider the better, I always say. It does help you remember things. All right. So we've agreed that it's cosine, right? Okay. So in this situation, then you would write. Now, some of you might want to write this, and that's okay. Hopefully, at some point you can get past this. Cosine theta is equal to adjacent over hypotenuse, right? And so cosine theta is cosine 30. The adjacent side is what we're solving for. That's my FAX. And the hypotenuse is 100. Okay? Pause there for a second. It seems that one of the problems that I have with students is that solving that is a problem. How do I get rid of, I got to isolate FAX, how do I get rid of divide by 100? Multiply both sides by 100. And we've been through this. You've got to be able to do that. So it's going to be FAX is equal to 100 cos 30. Now, is the FAX always going to be cosine? Yeah. No. Why not? Oh, that's well put. You could have your reference angle somewhere else, right? Yeah. Now, to be fair, 99% of the time, the reference angle is going to be above the horizon. So if it is there, is the FX always going to be cosine? Yeah. Yes. Very rare would the angle be this one in here, and then it would be right of vertical instead of above horizontal, right? Very, very rare is that ever there, and so 99% of the time, it's going to be cosine. Okay? So then you just take your calculator. Now, here's where some people have some problems as well. So try that on your calculator, and if you can't get it, make sure you ask. Don't wait till like the day of the test and say, yeah, I never did figure that out. That's a bad idea. Okay, guys, we got to shut that conversation down. Be amazed at how much you'll learn if you listen. Trust me. So try it in your calculator. Go 100 times. Now, some of you are going to go 100 cos 30 equals, and some of you are going to go 100 times 30 cos equals. And I don't know until I see your calculator, and you might not either, but you need to know which way to do it. Make sure you can get to 86.6. Calculator has to be in degrees. Okay, so check that. It's either going to be 100 times cos 30 equals, or 100 times 30 cos equals. Okay, and you're going to get 86.6. Okay, so if the angle, say, increases to 60 degrees, what happens to the FAX? Will it get more or will it get less? How come less? Yeah, not as much force as sideways, right? If it's up to 60 degrees, the FAX will decrease. So here we would write cos 60 is equal to FAX over 100. Can you, in fact, can you just write that step?
Yeah.
Some of you are going to realize that eventually you're going to be able to do just that. And that's what we usually do in grade 12. Just write 100 times cos 60. It's only 50 here. Okay? So if I increase the angle of pulling, it's not going to move as much sideways, which just makes common sense, really, right? Trying our calculator issues? Okay, we're just adding 1 degree of difficulty. So, have a force of 100 newtons. It is applied at an angle of 30 degrees above the horizontal to a 25 kilogram sled. Determine the acceleration if the surface is frictionless. So let's draw a free body diagram, and we're going to put our FA 100, and we've got an angle of 30 degrees. So this is my FAX, and there is no friction. It's going to when we do the acceleration, yep. In the second step, yeah. Yeah, it's going to. So your first step is to find FAX. Now, can I just do this? Are you okay with writing FAX is FA cos theta? Are you okay with that? So that's going to be 100 cosine 30. I think we already figured that out, didn't we? 86.6? Right? Okay, so that's the force. Now, technically, do I need to include weight force and normal force? In a free body diagram, you should. Are those having any effect on the horizontal acceleration? Usually the answer is no. Usually. Now, I haven't brought this up yet. Usually these two are equal. But now, and I'm foreshadowing a little bit here, down the road a little bit, if there's an FAX, what would that one be called? Or does that one even exist? Like if some of the force, some of that 100 goes sideways because you're at an angle, doesn't some of the 100 also go up? So what would you call that? Well, it's not the X component, it's the... Because I asked you, Jason. Well, you know me. The FAY, it's the Y component of the applied force. Now, does that mean that my Y forces are not balanced anymore? It might, right? Now, I'm just foreshadowing a little bit here, so don't freak out too much. But basically what I'm going to tell you is because it's frictionless, we're not going to worry about it just now. But we're coming to that. We're coming to that stage. So the FAX is the only thing that's pulling it sideways, and so therefore, my net force is my FAX, my F net X, if you will, right? The sum of all the forces sideways is just FA. How come? Because there's nothing else. And so my F net is, and that's equal to, of course, MA, right? Let's do it this way. Let's say F net is equal to 86.6. And then we're going to write F net is equal to MA. 86.6, the mass is 25, and that's where it comes into play to you, right there. And how do you solve that? 86.6 is equal to 25A. You have to get rid of times by 25, right? So you're going to divide both sides by 25, and your acceleration is going to be 86.6 divided by 25. we'll say 3.5 meters per second squared sideways. 2 steps. What do you think is going to happen to an example 2? What can I do to make it harder? Probably something. There clearly is an example 2. This time, you got the applied force, you got the angle, you got the mass, but this time there's friction. So I'm adding one more layer of degree of difficulty. This time there's friction. Shall we draw a picture? $50 newtons, 15 degrees. That's my FAX. And my friction force is going to be backwards. And it's going to be -5. So what does that -5, what does that friction force of -5 do? It's going to reduce the acceleration. So same steps. Find FAX, it's equal to FA cos theta. Write the formula. It's a way of me finding out from you, or you telling me, you selling me on how much you know. That's going to be 50 cos 15. $48.3. So before, the net force was equal to the FAX because there was no other horizontal force, but now there is another horizontal force. What is that other horizontal force? Friction force. So I got to add them up, right? Making sure one's negative. F net, and some of you might not like that I write X there, but that's okay. F net X, the net force in the X direction is equal to my FAX plus my FF. And that's going to be 48.3 plus -5, which I can do in my head, 43.3. And the last step, same thing as before, we're asked to find the acceleration. F net is equal to ma. F net x, I guess. So that's going to be 43.3. The mass was 30. A. So we can divide by 30. And I get 1.4 meters per second squared. Again, reminder, line up your equal signs, space out the steps, go from left to right, clearly identify your answer, include units, all good stuff. Any questions? Are we good? The nod of understanding? Do you want to try the last one on your own?
Yeah.
Oh yeah, okay. So I think all that's happening here is I'm taking that final step and I'm asking you to go a little bit farther with that. Try number 3. You guys have a whole sheet, don't you? Yeah, you have like the whole backside. Okay, so try it. See how you do, and then I'll give you the answer in about 5 minutes. Give it a try. Okay, so example number 3 says, a man pulling his 50 kilogram son on a 15 kilogram sled across an ice surface with a friction force of 2 newtons. Rope makes a 30-degree angle with the horizontal. He applies a 250 newton force on the rope for 3 seconds. Find the final velocity of the sled and the distance it travels in 3 seconds. Does this seem like a really big problem? It's going to have a lot of steps. That's because it's a really big problem and has a lot of steps. Let's start by drawing a picture. Applied force is 250. We have an x component, FAX. We have a friction force, FF. For now, let's ignore the y. Guys, just sit. Just don't. This is important, I've told you. You can get that in a minute. It's okay, man. I need you to watch this. You're missing out on all the good stuff here. Okay, so as before, our first step is to find the FAX. So hopefully you wrote FAX is equal to FA cos theta, which is 250 times the cosine of 30 degrees. $216.5. Okay, so we 1 mark for that. Now we got to deal with the friction. So F net is equal to FA plus FF. So that's going to be now, oh, hang on here, it's FAX. So that's going to be my 216.5 plus a minus 2. It's on ice, so it doesn't reduce the applied force very much. 214.5. Okay, so then as before, we're going to write F net is equal to MA. We're just building up the steps here. No. What's the mass? 65, right? They threw a little curveball in there. Right, you got to add those two masses together. So 214.5 divided by 65, you get an acceleration of 3.3. So that's as far as we went in the previous steps, but all of the rest is like stuff from the previous unit. Find the final velocity of the sled and the distance it travels in 3 seconds. That's like part B. So find the final velocity. Well, with acceleration, you can find the change in velocity. So 3.3. Change in velocity. The time is 3 seconds. You're going to multiply, right? 3.3 is equal to delta V over 3. You're going to multiply both sides by 3, and you're going to get delta V is equal to 9.9 meters per second. And is the initial velocity 0? It doesn't say that, but it doesn't say that it's anything else, so you can assume that. So that means, therefore, what? The final velocity is also 9.9. Right? 3 dots is fancy math words for therefore. Never seen that before? No? Yeah, 3 dots in a triangle means therefore. I don't know. Does that word even exist? Thereafter? It's not there before, it's therefore. I don't know. I'll have to think about that. Okay, so I now get the last step. I got to find the distance it travels. Do I just go 9.9 times 3? Sarah's not. She's shaking her head. How come, Sarah? I got to find average velocity. The only formula that's got distance in it is one that has average velocity, and we don't have average velocity. We have the VF. We have to go V bar is equal to VI plus VF over 2. At rest, final velocity 9.9 divided by 2. 4.95. And now the last step. V bar equals D over T. 4.9. This is basically a big giant review of everything we've done so far. Physics is like onions and Shrek. There's just more and more layers. We're just going to add them on together. I think I should make a poster. Put it on the wall. With Vinny's name on it. I like that. What? At home. 4.95. What was my time? 3 seconds. $14.85 meters. Well, let's see. 1, 2, 3, 4, 5, 6. Should we have one for the diagram? Maybe 7. Could you do it without the diagram? Yeah, you could. The diagram's not crucial. Yeah, maybe only 6. Okay, now I need to explain to you what all of those different sheets are. What's that? Yeah, if you haven't got one, go get one now so that I have something to actually explain. And I'll come get the last one there right away.